with some fancy thing, and some guys down the road with a calibrated stick. I don't know if you've ever seen those, but road construction does this all the time. Sectants can measure angles. It's kind of like a telescope thing that will measure the angle. And so like over here, if B's your tree, you can measure how high the tree is from an angle without climbing the tree. So what can I measure in this picture if that's a river? What's an important feature of that river I could measure simply by measuring theta and the distance along the shore? How wide the river is. Yeah. So there's some cool applications of trigonometry. Now that's my introduction into this section 3.6, right? The world we live in is not flat. And when we do these triangles, it's called planar, also known as Euclidean geometry, if you've ever heard of that. It's the geometry you learned in high school. It's based on putting it in a plane, meaning something flat. Well, if I were to go from here to, say, Santa Clara or Washington or Hurricane or something like that, it's not flat the whole way. Even if I were able to use tractors and stuff like that and flatten it out. Say you go to Kansas where people joke about it being flat. It's really not flat because isn't it on the earth? Think of a globe and it curves, doesn't it? And that's why they invented hyperbolic trigonometry to take care of the curvature of the earth. And obviously on the moon there's even more curvature and stuff like that. That's just a brief introduction as to the usefulness of hyperbolic trigonometry. Just think about, yes, we're still doing sines and cosines and stuff like that, but it's not in a flat plane. It's on curved surfaces. But all you really need to know for the homework, the book shows you graphs, and obviously the graph of sine, cosine, and tangent are important. I held you accountable to those. I'm not going to hold you accountable for a hyperbolic sine. S-I-N-H, that's how you read that. It's called the hyperbolic sine. But the book shows you the graph of the hyperbolic sine. It shows you the graph of the hyperbolic cosine. They don't look like the normal sine and cosine, do they? They're way different. What you do need for the homework, and this will prepare you for higher math, but only if you're like a math major and engineer, will you ever get to math 2280 on differential equations. We deal with these a lot. That's the next class where you're going to learn these. So we're just getting a taste of it. When I first saw it, most calculus books just have this in the appendix. They don't even have a full section on it. I was a little surprised that here in this book, all of 3.6 was on hyperbolic trig functions. Four teachers taught all this last semester. I haven't even looked at how two of them handled it because I thought I'm more like Castell and Jesse were the two teachers that taught out this book. So I was curious. I looked at their notes. Did they even teach 3.6? And the answer was yes. So I thought, well, I'm going to do it too. But I'm not going to test you on it. Maybe I'll give you a quiz, because on quizzes I allow you to use all your notes. So now I'm going to help you with what I expect you to know for both homework and possibly a quiz. The hyperbolic sine has a totally new definition. It's nothing like the normal sine, but it involves a difference of exponential functions over 2. The hyperbolic cosine is almost identical, except instead of a difference of those two hyperbolic functions, it's a sum. Now those other 4, I looked at those and it's like, I can remember that. I don't need notes because they're identical to the planar trigonometry. When I say planar, I'm talking about your normal tangent, cotangent, secant, and cosecant. This says the hyperbolic cosecant's the reciprocal of the hyperbolic sine. Isn't that true for the normal sine and cosecant? Right? So I could flip it, and the hyperbolic cosecant's going to be 2 on top, and the exponential's on bottom. This says the hyperbolic secant's the reciprocal of the hyperbolic cosine. Is that the same as normal trig? Yeah. This says the hyperbolic tangent is the sine over the cosine. Is that the same as normal trig? Yeah. And if hyperbolic cotangent's cosine over sine, doesn't that mean the hyperbolic cotangent's the reciprocal of the hyperbolic tangent? You can tell from those definitions, can't you? So I suggest you just focus on those two, because the other four, all you got to remember, same as normal trigonometry when it comes to reciprocals and ratios. These are reciprocals, those are ratios. They're identical for regular trigonometry. And then when it comes to the derivatives, let me see if there's any. Yeah, you're going to have homework derivatives. So let's jot those down real quick. But I'm not going to test you on these. So I don't expect you to have these memorized. Put them in your notes where you can refer to your notes when you're quizzed on this. That's all you're going to see from this. Your homework, your quizzes, if you haven't noticed by now, your quizzes are my way of keeping you accountable on the homework. Because if you don't do the homework, it's like, well, I don't know how to do this on the quiz. But if you do the homework, you come look at the quiz and it's like, I've seen this before, I can do it. And I allow you to use notes. So here we go, it's going to feel like 17, 18, 19, 20, 21, 22. It's like 6 more derivatives, but you will not have to memorize these. F of x, f prime of x. And the 6 new ones are simply hyperbolic trig functions. And all you need to add to make it hyperbolic is there's an h on the end of what we're used to seeing. So I'm going to write them in the normal order: sine, cosine, tangent, cotangent, secant, cosecant, cotangent, but they all have an h. Secant and cosecant, and they're hyperbolic. Now look at these derivatives, because it's surprising how similar they are to normal trigonometry. In fact, without even looking at the book, if I told you they're identical, they're not quite identical, but they're pretty dang close. If I told you they're identical to what we learned already on our memorized number 1, 2, 3, 4, 5, 6, I would say sine turns into a cosine. Cosine turns into a sine. Tangent is a secant squared. And I'm saying numbers 1 through 6, but I'm turning them into hyperbolic. In other words, I'm adding the h. Cotangent is a cosecant squared. Secant is a secant tangent. And cosecant is a cosecant cotangent. So nothing new there. Then we finish it up with the normal trig by putting minus sign on all the cos, right? So that one would get a minus, that one would get a minus, and that one would get a minus. That's where they're slightly different. Notice this one does not get a minus. So I'm going to put an asterisk on the ones that feel different. Doesn't that one feel different? We learned that the derivative of a cosine is a negative sign. When you do hyperbolic, it's a positive sign. That's why I'm putting an asterisk there. So do you see any other differences? Isn't that one different also? Yep. With normal secant, we need a positive over there. But with this one, it's a negative. So the two that are different are the ones that are reciprocals of each other. And aren't the other 4 identical? The cosecant starts with the cos, so let's put a minus, and they do have a minus, I think. Yeah. So that co has a minus, that co has a minus, but this co does not. So I put an asterisk on it. And this is not a co, it doesn't start with a co, but it had a minus, that's why I put an asterisk on that. So I just showed you an easy way to memorize them. Now let's look at how to do it.
Squared is also.
Oh, I forgot which is normal. Yes. We're not going to put an asterisk there, but it does need a minus.
So usually instead of all of the cos being negative, it's all of the reciprocals that are negative.
Yeah. Or I like to call them minors. These are the minor 3. There's another good memory aid. The 3 majors are all positive. The 3 minors are all negative. So when I say major, think of that as the ones on your calculator. Sine, cosine, tangent are on your calculator. The minor 3 are not on your calculator. I like that. The major 3 are positive, the minor 3 are negative. One other, then I'm going to be done comparing hyperbolic with normal trig. One other thing that's kind of cool is the sine and the cosine compared to the hyperbolic are the same at 0. you should know that the sine of 0 is 0. Well, look what happens on the hyperbolic sign. Don't you get 1 minus 1 over 2? That equals 0. The hyperbolic sign of 0 is 0. What's the normal cosine of 0? It's 1, right? Look what happens when you plug in 0 here. You get a 1 plus 1, that's 2 over 2, that also equals 1. So the hyperbolic sine and cosine are the same at 0. Doesn't that mean all 6 of them are the same at 0? Because tangent sine over cosine, these are derivatives. Anyway, they are all 6 the same at 0. I just discovered that.
The same curve doesn't take effect until you move beyond your origin.
Right. When x is something other than 0, then they're going to start giving you different answers. So
it's all based on frame of reference.
yes. The only ones I'll quiz you on then are 1 through 6, and then 26 through 41, and then we're going to move on. I don't care about this stuff 7 through 25. It's not useful to you even as you move on. But I think 1 through 6 you could handle, and it's really 12 problems because there's an A and a B. All you have to do on each of those is plug into the definitions. So the zeros we already talked about. Tangent was, let's go ahead and write the hyperbolic tangent. And if you remember, didn't it say it's the same as the ratio, sine over cosine? Well, if I want it in terms of our exponentials, that means it's e to the x minus an e to the negative x over e to the x plus e to the negative x. Because when I do this over this, can't you cancel the 2's? You see what I'm talking about on the algebra there? Those 2's are going to cancel. So this is a different I like this definition better than the one our book had. Our book said the hyperbolic tangent is equal to the hyperbolic sine over the hyperbolic cosine. So I just did the algebra of this over this and got that. So now if I'm trying to answer 2b, for example, 2b is going to equal, according to that definition, e minus e to the negative 1 over e plus an e to the negative 1.
So the e to the negative 1 switches. So positive e and negative e switch.
This minus and that in the top and the bottom you're talking about?
Yeah.
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 But you see how I got that from this definition? I just plugged in 1 for x.
Yeah.
Because we're finding the hyperbolic tangent of 1. Now to match the back of the book, there's a little bit more we could do algebraically. When you have a negative 1 power, it equals that. And that's a complex fraction, so I would times all 4 terms by what to get rid of the complex fraction?
E.
By e. Yeah. Top left, top right, bottom left, bottom right, times them all by e, and you get an e squared minus 1 over an e squared plus 1. That's probably the best answer for 2b, the hyperbolic tangent of 1. And they're all going to be pretty similar. What about 5b and 6b though? There's inverse hyperbolic. Okay, that's getting even further than I wanted to do. Let's look at 4b and then 5 and 6b. So to get 4b, I'm going to go back to this and change x to ln of 3. So I got an e ln of 3 plus e to the opposite of ln of 3 over a 2. Did I do that right? I took the definition and changed x to ln of 3. Right? Well, e ln of 3 is a 3. E and ln cancel. It'd be nice if I could get that negative out of the way so that e and ln would cancel again. Watch what I'm going to do with that negative. Aren't you allowed to take the coefficient and make it a power? Remember log property number 3? That's how you get the minus sign out of the way. So now can I cancel e and ln now that I took the negative and put it over there? Yeah.
1/3.
And you're left with a 3 to the negative 1, better written 1/3. That's right. Then you can multiply everything by 3 and you get a 9 plus 1 over 6. That's 10/6. That reduces to 5/3. Nice fraction. So 4b, we got an answer of 5/3, the hyperbolic cosine of ln of 3. So it's just a matter of definitions. Once you have those definitions, it's algebra work, isn't it? It's all just algebra. You're gonna need to be good at exponentials and logarithms. But to do 5b and 5b and 6b, we need more definitions, and I guess we could add that to the notes too. So there's the definitions of, it shouldn't, I'm not too terribly surprised to see LNs in the definition, because the normal hyperbolic sine and cosine have e's in them. And so it makes sense that the inverse of this would have the inverse of that, right? If we're going to do inverse on the left, we need an inverse on the right, and the inverse of an E is an LN. Now the rest of that gibberish is kind of, I have no idea why it's all of that. But remember, I'm not going to test you on this, but I probably will quiz you on this. And same with those derivatives. So I'm not even going to take the time to write those. I know a lot of you are writing those. You need those in order to do 5b and 5c, don't you? Because 5b asks what's the inverse hyperbolic sine. Now that's a mouthful, but that's how you read this. This means inverse, that means hyperbolic. So it's an inverse hyperbolic sine of some number. Just take that definition and plug in whatever number they ask for. If they wanted the inverse hyperbolic sine of 0, you could plug in 0 and you're going to get an ln of 1. And ln of 1 is 0. Well, that makes sense, because didn't we already say that if I plug in 0 here, I get 0 over there? So with inverse, the two trade places. And when you trade 0, 0, you still got 0, 0. What was, remember the one we did and we got an answer, wasn't it 3/5? I think we had an hyperbolic cosine of ln of 3. Was that the last problem we just did that turned into 3/5? It was 5/3? Yeah, I knew was it. That's why I was asking you. So one of the problems took this and we got that, correct? So do you understand? I'm checking your algebra knowledge then. If that is true, which when you change my 3/5 to 5/3, I think it's true. You know how that relates to this? We should be able to plug in what for x from that? Shouldn't we plug in 5/3 here and get back what? ln of 3. Right? Isn't that how inverse trig functions work? Inputs and outputs trade places. So that would be a good test to see if you're understanding this. Well, let's plug in a 5/3. 5/3 squared is 25 over 9. Minus 9 over 9. Say I'm pointing to 1 and I'm saying 9 over 9. That's how you get a common denominator, right? So I'm plugging in 5/3. I want to do the inverse hyperbolic cosine of 5/3 because I want to see if I understand this section, basically. This is just a good self-test. I got 5/3 doing something totally new. Now I'm doing something else totally new, but I know inverse functions should trade inputs and outputs. So I'm hoping that when I do this, I get an answer of ln of 3. 25 over 9 minus 9 over 9 makes 16 over 9, and the square root of 16 over 9 is 4 over 3. Right? Hopefully you followed that. I need to add 5 over 3 to 4 over 3. Doesn't that make 9 over 3? And 9 over 3 is 3. Is that what we were hoping for? Isn't that cool? That's about all I expect you to understand on all of these, and is how to use them. And I'll put a few of those on a quiz, so if you take good notes, you'll be fine. If you didn't have time to write those down, you all got a copy of a book. Just look it up. It's in section 3.6. Because the last ones deal with these 6. So now that I have those 6 in my notes, 26 through 41 is 16 problems, and I should be able to handle any one of those 16. 31 is the only one I see in blue. Let's try that one. So the directions say find the derivative, and then simplify it. Well, if y is equal to e to a hyperbolic cosine of 3x, that sounds like a chain rule. E to the u has as its derivative e to the u times a du. Now the du needs another chain rule because it's not just hyperbolic cosine of x. It's got a 3x. So if you know what I mean by double chain rule, there's going to be a 3 at the very end in there. That's the second du. But our first du, I call that e to the u. So du means the derivative of the hyperbolic cosine. Don't we have that over there? The derivative of hyperbolic cosine is a hyperbolic sine. Of what though? What's going to go in there? 3x, yeah. The input doesn't change when you do the derivative. Then I don't know why I did that out of order. I just wanted to hurry and write it down before I forgot because I said there's a double chain rule. The 3 comes from the derivative of 3x. It's a second chain rule. That wasn't that hard. Even though it's totally new, this is what's new. But if you're good at chain rule, you could take what's over there and get this answer pretty easy. So I don't think it's all that big a deal. How about 34? So 34 looks like a chain rule. The derivative of a hyperbolic sine, according to that, is a hyperbolic cosine, followed by a hyperbolic cosine of x. Now don't I need to times that by the derivative of the inside? And the derivative of the inside is a hyperbolic sine of x. One more, number 33. F prime of t. Before I start differentiating secant, isn't that a secant squared? So don't we need a chain rule? We're going to call that u squared. The derivative of u squared is a 2u to a power of 1. Then I need a du, meaning the derivative of what? What was u representing when I said that's u squared? Isn't u what's being squared? The hyperbolic secant, right? So if that's a u squared, du means the derivative of the hyperbolic secant. And I look over there, and the derivative of the hyperbolic secant is a negative hyperbolic secant. I forgot an x there, didn't I? It should have had an x there, times a hyperbolic tangent. All right, so I said u squared has a derivative of 2u to the 1 du. Is there another chain rule? There is. In order to just be one chain rule, that would have to be just t, right? But anytime it's more than just t, you got another chain rule. So there's a second u. The first u is secant, hyperbolic secant. The second u is e to the t. So doesn't that mean I need to differentiate e to the t? Which we all know is what? E to the t, and then an easy one. So there's your second chain rule, and there's our answer. You could, wait a minute, should these be e to the t? I think they are e to the t, aren't they? I was looking over there and I just recopied that, but we weren't doing a hyperbolic secant of x, we were doing a hyperbolic secant of e to the t. So we got a negative, we got a 2, and then I see the same thing multiplying, so secant times secant is going to be a secant squared. And you know I mean hyperbolic secant squared. And then you got a hyperbolic tangent. So I know this is weird, I've had seeing those h's and stuff, but don't let it confuse you too much. It's not all that different. That's what I would expect for the back of the book answer. And this is 3.6, number, the first odd one I chose to do. What was it, 33? Was it 33 you just did? 3.6, number 33. Okay, look where my finger is. Does that match what we ended up with? A negative 2 e to the t secant squared times a tangent. Is that right?
You're missing an e to the t.
Miss it, I was afraid of that, but I didn't miss it here, right? I had it, I forgot to write it there. That's why we love the back of the book, to catch those stupid mistakes. I had it, I just forgot to write it. You guys should have got that. So yeah, it matched the back of the book, and you can do the same. You can tell I'm excited to move on to the next section. Well, whether you can tell or not, I'm excited to move on to the next section, okay? It's called L'Hopital's rule. 3.7. So let's get some notes to develop what this French mathematician L'Hopital proved. 3.7 is on L'Hopital's rule. And right off the bat, I'm going to give you this rule. It's a new trick for doing limits. So he said that if a limit, as it doesn't matter what x is approaching, let's just say x approaches a. So we got a limit of x approaching a. And we're taking the limit of some fraction. And we're going to have an f of x in the numerator and a g of x in the denominator. So there's our rational function. It doesn't even have to be a rational function. A rational function means f and g are polynomials. It works whether they're polynomials or not. So let's just call it a ratio of two functions. They don't have to be polynomial functions. So if that limit turns into a 0 over 0, now did we ever see those? Like all the time, right? We've seen 0 over 0 a lot. But here's another one that we saw less. L'Hopital's also works if you get infinity over infinity. Now, it doesn't work in any other situation, so that's important for me to emphasize right here and now. You got to have a 0 over 0 or infinity over infinity for L'Hopital's rule to work. Now, I invented an adjective, and I like to say, if you see this or this, it's L'Hopitalable. You like that word? That means you could do L'Hopital's rule. So what if you see 0 over 6? Does that fit one of those? No. 0 over 6 is not L'Hopitalable. What if you see infinity minus infinity? Does that match one of those? That's not L'Hopitalable. You have to have either this or this to be L'Hopitalable, which means to do L'Hopital's rule. And L'Hopital's rule, you know how theorems finish. They have an if part followed by what? What goes along with if? Then. Any computer programmer should know that really well. Computer programming has ifs, then statements. So then we conclude that that same limit can be found by, instead of evaluating f on top and g on bottom, you do f prime on top. I need to put a limit in front of that, sorry. We're still going to do a limit as x approaches a. You still do a limit as x approaches a, but you get to do f prime on top, f or in g prime on bottom. Okay, a lot of you might feel a little rusty on limits. Am I a little bit accurate on that? I've heard some of you say, yeah, I forgot limits already. Oh, well, we need to refresh that, okay? I'm going to give you an example of this. Let's do a limit, and I want for my fraction x squared minus x minus 6. And how about an x on bottom, x squared minus 9. And we'll do a limit as x approaches 3. So, those of you that think you forgot limits, here's your refresher. We always do direct substitution first. And in this case, you're going to get 9 minus 3 minus 6, and that's 0 on top. And 9 minus 9, 0 on bottom. So in the past, we said, okay, 0 over 0 means I need to do an algebra trick. And isn't the algebra trick we do there is factoring. You factored x minus 3, x plus 2. And on bottom, x minus 3, x plus 3. And do you get excited at this point when you see the x minus 3 on top and bottom? That's good news, isn't it? Because now our 0 over 0 is gone, and we get an answer by redoing the limit as x approaches 3. And what's our answer then? After canceling, you get what? 5 over 6, and that's right. And you can see it numerically. That means plug in a 2.99999, and you're going to get something really close The decimal for this, I think, is 0.833333, or you could just say 56. And if you do 3.00001, you're also going to get something super close to 0.8333. Remember all that now? Okay, now for this new theorem. When I plugged in 3, did it end up being L'Hopitalable?
Yes.
Well, that's right. Why? We got a 0 over 0. That is L'Hopitalable. So here's what we write in our notes. You put an arrow and you put an L on top of your arrow. And guess what that L stands for? L'Hopital's. It means I'm doing L'Hopital's rule. And L'Hopital's rule says I'm going to redo that same limit, but not with F and G. Instead, we're going to do F prime. Does that look like F prime? Derivative of the top? So what am I going to write on bottom for G prime? 2x, right? And now let's plug in 3, and you get 2 times 3 minus 1 on top, and 2 times 3 on bottom. Is that giving us the same answer? Do you see it? 6 minus 1 on top, 6 on bottom. It's a whole new way of getting it. Isn't that cool? It's way cool.
Right.
You want to see something else that's cool? Here's one that we basically just memorized. The limit as x approaches 0 of sine of x over x. And I'm hoping maybe a handful of you might still remember that one. Direct substitution gives you 0 over 0, doesn't it? Does anyone remember what the answer was? We did that before and we had homework on it and we just memorized it. Not a single one of you remember the answer to that? Well, you're lucky because with L'Hopital's rule, you don't have to have it memorized anymore. And I could tell a lot of you are like, we've never seen that before. I beg your pardon. It was back when we first learned the squeeze theorem. Now, I know you remember the squeeze theorem, don't you?
Yeah.
So, does anyone remember what section the squeeze theorem was? Well, I don't.
Isn't it 1?
It's chapter 1, 1 point what?
I think it's 3.
1.3?
She's talking about the limit. The limit is
Oh, the limit's 1?
Isn't it 1?
this.
Yeah.
Yes, it is. Okay, I found the squeeze theorem. So this is section 1.4. They're using theta instead of x. So is it Anna? No.
Yeah.
Anna. Anna remembered it. But this is page 42. Section 1.4. We've seen that before, and none of you remembered. And I don't care that you don't remember anymore, because now L'Hopital's is going to get it for you. As soon as sine of 0 is 0. And as soon as you see that 0 over 0, we have a new way. Rather than just memorizing that it's 1, you do L'Hopital's rule, and then we're going to redo that limit. What's the derivative of the top? Isn't it cosine?
Yep.
Derivative of a sine is a cosine. What's the derivative of the bottom?
1.
So redo it. Cosine of 0 is, see how we're getting the answer of 1 now using L'Hopital's rule. Where before we just accepted it, either that or you read all that squeeze theorem, which I didn't make you do, which had a ton of geometry. L'Hopital's rule is awesome. Let's do one other. Probably the hardest of the 0 over 0 limits we had to do, wouldn't you agree, was using the conjugate trick with the radicals. Remember those beasts? I don't know if I could even make one up. Let's see if I could. How about the limit of the square root of 2x minus 5? No, minus. What do I want here? Let's do a limit as x approaches 5. And then we'll have 2x minus 1. Subtract a 3. All over x minus 5. Okay, so direct substitution, do you see what you get? Don't you get a 3 minus 3 on top? Do you see why 2 times 5 is 10, minus 1 is 9, squared 9 is 3. It's 3 minus 3 on top, isn't it? 5 minus 5 on bottom, isn't that a 0 over 0? So it's L'Hopitalable, isn't it? But just to help you appreciate L'Hopital's rule, let's do it the old school way. Because we did these before. You remember? Before we did L'Hopital's, we did these. And I called it the conjugate trick, right? And there's some multiple colors. So we do square root of 2x minus 1 with a plus 3, and you times the bottom by the same thing. And then on top, a minus b times a plus b is equal to a squared minus b squared. And on bottom, I'm just going to leave that x minus 5 together with a square root of 2x minus 1 with a plus 3. We've done this before. The top's a 2x minus 10. You could factor out a 2, and you're left with x minus 5. Did you follow that? Negative 1 and negative 9 make negative 10. So I factored out a 2. And there's the magic. That x plus 5's canceling. So now I no longer have a 0 over 0. So in fact, we have a 2 on top. And on bottom, when I plug in a 5, you're going to get 3 plus 3. So the answer is 2, 6. That reduces to 1/3. That's the old way of doing it, right? So I'm going to leave that 1/3. I'm going to erase the old way and see if we like the new way better. I'm hoping we do. Okay, direct substitution gives you 0 over 0. So I'm going to do L'Hopital's rule. Now this one's a little bit harder. We need a chain rule, but you should be good at chain rule by now. U to the 1/2 needs a 1/2 u to a negative 1/2 with a du, and the du's 2. And the derivative of 3 is 0. The derivative at the bottom is a 1. So now I'm back to that limit with x going to 5. 10 minus 1 is 9, square root's 3, negative power gives me 1/3. So I got a 1/2 times a 1/3. The 1/3's the hardest part, times a 2. The 1/2 and the 2 cancels. I don't know about you, but I like that way better. They both gave us 1/3, and L'Hopital's rocks. And so far we've done 3 or 4 L'Hopital's. Each started out with a 0 over 0. But if you read the notes, there's another problem where L'Hopital's works. And that's not only 0 over 0, but what else? Infinity over infinity, yes. Now this one you may not like L'Hopital's as much because I touch an easy way to do these. What if you have an x squared minus 5x cubed plus 7 over 2x cubed minus 6x? So when you plug in infinity, you get negative infinity over infinity. By the way, they could be positive or negative. It doesn't have to be positive infinity over positive infinity. Who remembers the shortcut trick that I taught you on that? I broke it up into 3 cases. The 3 cases were what? Top heavy, or bottom heavy, or same degree, right? So let's review those real quick, because this was, I know you guys liked this. It was a shortcut. It wasn't very theoretical, but whenever it's bottom heavy, what do we write for the answer?
0.
And that's only true if x is approaching what? Infinity, right? So when x goes to infinity, if it's bottom heavy, you get a 0. Is this one bottom heavy?
No.
So it's not 0. If it's top heavy with x going to infinity, the answer is always what? One of 2 things. You forgot that one? What?
1? Or is it the 1?
That's like
On top heavy.
Highest power.
Yeah, the top's going to have a higher power than the bottom, but with this limit, what's your answer if it's top heavy? Yeah, infinity, or maybe negative infinity, right? Could be positive, could be negative. That's right. Is this one top heavy? No. This is the 3rd case, right? So what do we do when it's same degree, 3rd degree over 3rd degree?
It's coefficients over.
And the answer is
negative.
-5 over 2, right? -5 over 2. Yep. Okay, I can tell most of you kind of remember that top heavy, bottom heavy, same degree trick. I don't think L'Hopital's is going to make this one any easier, but it will give us that answer. Because when I plug in infinity, really you just got to look at the dominant terms. That's not a new trick, is it? Those are the dominant terms, and you got a negative infinity over infinity. But that's L'Hopitalable. according to that. So I take the derivative of the top and the derivative of the bottom, and then we repeat, meaning we're going to plug in infinity again. Isn't it same degree again? But if we do L'Hopital's way, you get negative infinity over infinity again. So we're going to follow with L'Hopital's rule and get a 2 minus 30x over 12x. And then you're going to get infinity over infinity again, really negative infinity over infinity. So what this teaches you is sometimes you have to do L'Hopital's again and again. But finally, the derivative of the top is negative 30, the derivative of the bottom is 12, and what does that reduce to? Negative 5 over 2. Isn't that cool? Okay, so the other things that we're going to have to cover on Monday, because we're out of time, there's some indeterminates that are not L'Hopitalable. I think that's a good way to write this. Indeterminate means the answer could equal anything. You know infinity over infinity and 0 over 0 could equal anything. But these are indeterminates that are not L'Hopitalable. I don't do French very well. I don't get that capital L apostrophe capital H. Sometimes I even see this little caret above the O, but I just say it's French to me. Indeterminates that are not L'Hopitalable. There's 3 of them. There's the order our book gives them are products, differences, and powers. Write those in your notes, and maybe I could give you just a quick example. Products, differences, and then powers. And the indeterminate products are one that I could think of right off the top of my head is 0 times infinity. Now, what does indeterminate mean? If you see 0 times infinity, what could that equal? It's indeterminate, therefore it could equal anything. It might be 2/3. And differences, infinity minus infinity, that could equal anything. Powers, there's like, boy, this book's not as good as the last one I'm used to. I'm going to have to look. No, here I found some. 0 to the 0 is an indeterminate power. Infinity to the 0 is an indeterminate power. And 1 to the infinity is an indeterminate power. All of those could equal anything. But are they L'Hopitalable? No. So I'll show you how to handle those on Monday. And I meant to say L'Hopitalable. Those are not L'Hopitalable, because they're not 0 over 0 and 0 over 0. You get it? It's going to be a beautiful weekend. Enjoy it. We'll see you on Monday.
Things I should be doing today. I will let you know if you have questions still.
All right, awesome. Thanks, man. I appreciate it.
Thank you.
Oh, yeah. Yes, right. Yeah.